Welcome back. Today I'd like to talk to you about the mean value theorem. And the mean value theorem section is actually a section about 4 different theorems. So we're going to talk about these 4 theorems today, and they each help us prove the next. And so one thing that's kind of cool about this lecture is it's very mathematical. Like, this is very much what it's like to take a mathematics course. And I want to just quickly run through the 4 theorems that we'll be talking about today. And I'm actually going to prove these theorems for you, and then we'll work out some homework-like problems that you would use these theorems to do. But the 4 theorems today that I'm going to talk about are the following. First is what we call Rolle's theorem. The second is called the mean value theorem. And sometimes we call the mean value theorem for short. And then we get to the zero derivative theorem. And then we have what we call the constant difference theorem. Okay, so we have these 4 theorems that we're going to prove today. And I'd like you to actually take a look at these proofs because they're, first of all, interesting. And it kind of shows how math works. And this is one of those days of calculus class where it's kind of like, is a math major kind of my thing? Would I like to be a math major? And if you like the kind of thing I'm doing today, you would really enjoy probably mathematics and being a math major, because it really is about proving theorems in math, more so than it is doing integrals, okay? You need to be able to do integrals, but that's not really what math's all about. So if you really like this lecture, you might say, hey, maybe a math major or a math minor is right for me. If you don't enjoy this lecture, you might think, well, I might steer clear of a mathematics major if I don't like proofs and I don't find them interesting. Okay, so that said, let's get started with our first theorem, and that is Rolle's theorem. So I've written out Rolle's theorem for us to look at, and so let's go through it really quick. Rolle's theorem says, suppose that f is continuous on a closed interval from a to b and differentiable on the open interval from a to b. If f of a is equal to f of b, then there exists at least one number c between a and b where the derivative of the function at c is 0. Now, let me draw a quick picture of this just so you can get a feel for what's going on here. So we have, let me draw my x and y axis real quick here. And we have a point A, we have a point B, and what we're told in this theorem is that the functional value of A and the functional value of B are the same thing. So we have f of A up here, f of B up here. They're the same point. And what it's saying is, if this is a nice continuous differentiable function on the interval, then somewhere the derivative is 0. And I think this is true because I challenge you, start drawing a function from one side to the other where you don't draw at least one spot where you have a horizontal tangent line, okay? So you can't do it. There's going to be at least one point in between A and B if you draw a nice continuous differentiable function that has a derivative of 0, no matter how you draw it. Okay, so that's what Rolle's theorem says, and now we'd like to take a minute and actually prove Rolle's theorem. And the way I'm going to do it is, let me kind of draw a picture of how I'm going to do it, and then we'll actually write it out. Well, the first thing is, the simplest way that this function could look is here's A, here's B, here's f of A, here's f of B. Well, it could just be a straight horizontal line. Now, if it's a straight horizontal line, every point has derivative 0, so that's not very interesting. So in other words, if f is a constant function and it's just nice and constant, there's really nothing to do here. The more interesting thing is when it's not constant. And if it's not constant, then we know something about that function. We know that it either goes up or it goes down. And that means that it either must have an absolute maximum or an absolute minimum. And wherever it does, I think that that's going to be our special point. So let's actually write this down as a formal proof so you can see the proof. So I'm going to erase this really quick, and let's get to the proof. So proof of Rolle's theorem. So I know that f is continuous on the interval, closed interval from a to b. So f must have an absolute max and absolute minimum on the interval a to b. Okay, this is something that we showed before. Our extreme value theorem says that, hey, if you've got a nice continuous function on a closed interval, it has to have an absolute max and min. And we spent some time a couple sections ago just showing this, right? That we could find these absolute max and mins on closed intervals. Okay, so now that we know that it has to have an absolute max and min, I said that there were two cases. So I'm going to break this into two cases. And case one is going to be that f is constant. So if f is a constant function, then what is its derivative? Any constant function has derivative 0 at all points. So that means then we have that f prime of x is equal to 0, and we are done. We don't just have one point where the derivative is 0. Every point's derivative is 0. So we've got at least one point where the derivative is 0. So we're done. So if f is constant, there's a place where the derivative is 0. In fact, everywhere. So let's move on to case 2. And in case 2, f is not constant. Okay, so if f is not a constant, then the absolute max or min of this function f occurs at a point C, and that C is in the open interval from a to b. In other words, it's not at a and it's not at b. The reason why is, remember that the functional value at a and the functional value at b are different. So there's either going to be some point that's bigger than a and b, since this is not a constant function, or there's going to be something smaller. So the absolute max and min can't both be the endpoints. So there's some point in between a and b that's either the absolute max or the absolute min. But as soon as I know that, well, where do I know that these absolute max and mins can happen? We talked about this before. Absolute maximums and minimums can happen at endpoints, and they can happen at critical values. And so if it's not an endpoint where this absolute max or min is happening, we can say, so C is a critical value. And what do we know about critical values? We know that critical values have derivative value of 0. And we know that the critical value doesn't have an undefined slope because we said it was differentiable. So that means that f prime of C is equal to 0. And we're done with our proof. Okay, so this proves Rolle's theorem that says that if you have a continuous function on a closed interval, a differentiable function on an open interval from a to b, and if the endpoints have the same functional value, somewhere in between the derivative is 0. And that's what we just proved. Okay, so that's the end of the proof of Rolle's theorem. All right, now we'll talk about the mean value theorem. And so let's talk through it real quick. So the mean value theorem says that if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there exists in the open interval from a to b at least one number c such that f of b minus f of a over b minus a is equal to f prime of c. Okay, so we call this the mean value theorem, and let me tell you basically what the mean value theorem tells us. So let's draw xy axis, and we have some value a over here, we have another value b over here, we have f of a up here, f of b maybe down here. Notice that unlike Rolle's theorem, these two values do not need to be the same thing. And then we have some function in between. So let me just draw something. How about something like this? Okay, so here's our function. Now, if our function looks something like this, what this is saying is, well, what is f of a minus f of b over b minus a? That's the slope between these two endpoints. Okay, so we've got this slope, f of b minus f of a over b minus a, this guy right here, that's a slope. It's a slope of what we call the secant line between these two endpoints right here. Okay, so we've got these two endpoints, and they have a slope in between them. What the mean value theorem tells us is there's another point in between a and b where the slope of the curve is equal to the slope of the secant line. So maybe this is our point C, where the slope of the function is the same as the slope of the secant line. Okay, so that's what the mean value theorem says, is if you have this nice continuous differentiable function, then there's a slope between the endpoints, and somewhere between those two endpoints there's another point where the slope of the function is the same as the slope of that secant line. That's what the mean value theorem says. Okay, so let's go ahead now and prove the mean value theorem is true. All right, and to do this, we're going to get a little bit clever. All right, so let me erase this real quick, and let's prove the mean value theorem. So proof. So what I'm going to do is I'm going to make up a new function, and I'm going to let this new function help me to prove the theorem. So let's let g of x be some new function, and I'm going to define it this way. G of x is going to be f of b minus f of a divided by b minus a times x minus a plus f of a minus f of x. Okay, so here is my new function, g of x. And notice there's a couple x's that show up. There's an x minus a in the first piece, and then there's this minus f of x in the second piece. And that's what we would plug in for if we plugged in something for x into g. Okay, now what I want to do now is let's look at g of a and let's look at g of b. Okay, so first of all I want to say, well, what in this case is g of a? And if I plugged in a here, what happens? Well, I still get this f of b minus f of a over b minus a times a minus a. Well, a minus a is 0. So this whole thing is just going to be 0. But I still have plus f of a minus f of, well, this is an x, so I plug in a. So I get f of a minus f of a, and that's also 0. So I just end up with 0. So g of a is 0. Great. Okay, let's look at g of b. So g of b is f of b minus f of a over b minus a times b minus a plus f of a minus f of b. Okay, so first of all, I've got a b minus a over b minus a here, so that b minus a cancels with that b minus a, and what am I left with? I'm left with f of b minus f of a plus f of a minus f of b, otherwise known as 0. So g of a is 0 and g of b is 0. This should kind of ring a bell in your mind. Hey, didn't we just prove something about functions who have their endpoints being equal? Yeah, Rolle's theorem applies to this function g. It's nice and continuous, it's differentiable, and so let's look at what does Rolle's theorem tell us then? Since g of a and g of b are the same, there must be somewhere in between a and b where the derivative of g is 0. That's what Rolle's theorem tells us. Okay, so let me move on real quick. So that means there exists a value c in the interval from a to b such that g prime of c is equal to 0. Okay, so let's think for a second about what the derivative of g actually is. Remember, g of x is f of b minus f of a over b minus a times x minus a plus f of a minus f of x. So if I take the derivative of that, I get that g prime of x is equal to, well, this whole thing right here, that's just, that I just circled, that's just a constant. So I've got this constant times x, and the derivative of constant times x is just the constant. So I get f of b minus f of a over b minus a. F of a, that's just a constant, so its derivative is 0. And the derivative of negative f of x is negative f prime of x. And I know that at c, this derivative is 0. So if I say g prime of c, then I get f of b minus f of a over b minus a minus f prime of c is equal to 0. So now I move the f prime of c to the other side of the equation, and I get that f of b minus f of a divided by b minus a is equal to f prime of c. And that's exactly what I wanted to happen. This is saying that the secant, the slope of the secant line, which is this guy, is equal to f prime of c for some value c in between a and b. And so the mean value theorem is proved. Now for the zero derivative theorem. The zero derivative theorem says if f is a continuous function on the closed interval from a to b and is differentiable on the open interval from a to b, with the derivative of f being 0 for every x on AB, then f has to be a constant function on the closed interval from a to b. Okay, so let me just describe the scenario here. We have a nice continuous function. I can take its derivative, and all the derivatives are 0. Then we're saying that f has to be constant. Now, it's really easy to see that all constants have derivative 0. But does that mean that everything that has derivative 0 is a constant? And the answer is yes, based on the zero derivative theorem, that everything that has derivative 0 everywhere is constant. That's not obvious. Maybe there's some really, really funky function that it would take 14 pages to write the function, but lo and behold, the derivative is 0. Well, that's not true, and the zero derivative theorem tells us that. So let's prove the zero derivative theorem. Now, to prove the zero derivative theorem, I've got to first understand, what does it really mean for a function to be a constant function? And the answer is that to be a constant function, you really need to say that any 2 points in the interval have the same functional value. Now, it doesn't matter which 2 points I choose. In fact, all of the points need to have the same functional value. But you have to buy my story for a second logically, that if any 2 have the same functional value, then they all have the same functional value. So if I can choose any 2 randomly and they'll always have the same functional value, then all of them have the same functional value. Okay, so what I'm going to do is I'm going to start my proof by taking an x sub 1 and an x sub 2 in my closed interval from a to b. Okay, so if I take any 2 points in that closed interval, I'd like to show that their functional values are the same. Well, to do that, what I'm going to do is I'm going to say, oh wait, this is a nice continuous function, it's differentiable, so the mean value theorem applies on the interval. The mean value theorem applies on the interval from x1 to x2. Okay, and what would the mean value theorem tell us? The mean value theorem would tell us that there exists a c in the interval from x1 to x2 such that we have that f of x2 minus f of x1 over x2 minus x1 is equal to f prime of c. But what did I say already about the derivatives? All of the derivatives of this function are 0. So f prime of c is 0. But if you look at this equation looking from left to right, I've got that f of x2 minus f of x1 over x2 minus x1 is equal to 0. Well, when is a fraction 0? If the top is 0 or if the bottom is 0? The answer is when the top's 0. So that means that the top of that fraction, f of x2 minus f is equal to, let me back that up a second. F of x2 minus f of x1 must be equal to 0. But if I move the f of x1 to the other side, I get that f of x2 equals f of x1. In other words, the two functional values are the same. So take any 2 points in between a and b, and what I'm telling you is that their functional values are the same. And that's exactly what it means to say, therefore, f is constant. And we're happy. Okay, so that is the proof of what we call the zero derivative theorem. And the zero derivative theorem simply tells us that if a function's derivative is always 0, then the function itself is a constant. Now for the constant difference theorem. The constant difference theorem says the following. So now we have two functions. We have a function f and we have a function g. and function f and g are both continuous on this closed interval from a to b, and they're both differentiable on the open interval from a to b. Okay, and then it says that, let's say that both of these functions have the same derivative, that f prime of x is equal to g prime of x for every single x in the open interval. Then there exists some constant c such that f of x equals g of x plus c. In other words, f of x and g of x are almost the same function. They only can differ by a constant value, like 3 or 7 or something like this, some constant. Okay, so that's what the constant difference theorem says, is that if two functions have the same derivative, then they're the same function other than adding a constant. All right, so let's prove the constant difference theorem. And to prove the constant difference theorem, I'm going to use another clever function to help me. Okay, so what I'm going to do is I'm going to let h of x be equal to f of x minus g of x. Okay, now let's take the derivative. So h prime of x is equal to f prime of x minus g prime of x. Okay, now we know that f prime of x and g prime of x, those are the same thing. We said that f prime of x is equal to g prime of x, so this is equal to 0. But wait a second, what do I know? If a function's derivative is always 0, we just said that the zero derivative theorem tells us then the original function must be a constant. Okay, so let's take that into consideration right now. We have that h of x then is equal to a constant, c, because of the zero derivative theorem. Okay, so we have the h of x is equal to 0. What was h of x? Well, h of x was f of x minus g of x. And we know now that that's equal to c. And if I just rewrite that a little bit, I get that f of x is equal to g of x plus that constant c. And that's exactly what I wanted to show, is that the function f of x was just equal to g of x, possibly plus some constant. And that's the end of these 4 proofs that I wanted to do for you. And so now let's look at some example problems.